Hi and welcome. This is the first part of the two-part series where I evaluate a bunch of different calipers, including one that was given to me to evaluate by Shars. This first part, I am going to build a holder for gauge blocks that allow me to hold an adjustable quantity of gauge blocks together so that I can have a test fixture to test the calipers. It will be designed with a screw on one side to tighten, to push against, with a pushing block that'll push against the gauge blocks with a stop block on the other side. Let's just get into it. Hi and welcome. So before we get started on the big caliper showdown, I need to make a holder for my gauge blocks that once you ring them together, you can hold the cluster together so that you can measure them with a caliper repeatably. But before I can do that, I have to surface this stock and get it to size. I'm just going to use my new cutter, my new face cutter that I got from Shars here. It was fairly inexpensive and the quality seems excellent. I want to try it. I have never used it. I thought it'd be a good opportunity also to cover some really basics of cutter geometry, since I'm by no means an expert. But you will notice significant differences between some cutters. So with this cutter, I think you can see pretty easily that the angle, the whole top plane is leaning down. That's called a negative rake, and it gets a good finish, but it takes more power to cut. This one is a slightly negative rake, a little bit of negative rake, but pretty close to neutral. This one takes less power than the other one, may not get quite as good a finish. I'm really not certain about the finish related to rake. I noticed that all the larger holders intended for more powerful machines are negative rakes, so there's got to be a good reason for it, and I've heard stories that it improves the finish. I really need to compare. I intend to talk to some of the manufacturers, see if I can find out some better information about that. Then there is this cutter here. Now this cutter is also a negative rake. You can tell it's sloping down, but the insert itself turns this negative rake into a positive rake, and this is an aluminum cutting insert. You can tell it's very shiny and polished so that the aluminum will have less chance of sticking to it, and a positive rake and a very sharp cutting edge. So cutters themselves can convert a negative rake cutter, the carbide inserts can turn a negative rake cutter into a positive rake so that it takes less power and does a better job of cutting soft metals like aluminum. So I have two inserts for this cutter head here, and one of them is for steel, this one here, and the other one is for aluminum. You can tell, again, much shinier surface, and you can tell that it sticks up more and it's getting more of a positive rake even the other one. And I think on this cutter, since it's such a large diameter and there are so many cutting points, that a positive rake will take less power from the machine. Now, I have a 3 horsepower mill, so it probably shouldn't be a problem, but it's interesting to note that that you can try and compensate for weaknesses in the machine just with the cutter geometry. Also, the finish on aluminum should be much better with a positive rake cutter on it. So I'm going to set that up. We're going to surface some stock. We're going to build the holder for the gauge blocks, and then once we're done with that, we can compare all of these calipers and see how Shars' new designed in America caliper compares to some of the big boys. Like this is an Etalon made in Switzerland. I've got several Michu Toyos. And I have a Fowler, also made in Switzerland. And this is their Ultra Cal 5. This is their high-end one. So let's see how they all fare, and I want to check a bunch of different features about them. I want to check jaw hardness, because that's actually really important, because a lot of us use the jaws to scribe on softer metals lines. So if they're not hardened, they're going to wear right off and you'll screw up your measuring surface. Now, I wouldn't take my best ones and do that with it, but my everyday, my favorite go-to ones, which are these 4-inch ones, I do use them to score sometimes just to get a reference mark on the surface. So let's have at it and see what happens. All right, so here it is, fully loaded with aluminum cutting teeth. You will notice that it's sort of a neutral rake here, and then you add the inserts and it makes a very positive rake, which on a cutter with this many cutting positions probably needs to be, especially if you're covering the full surface of the cutter. So if you're doing something, this is a 3-inch cutter, so if you're doing something 3 inches wide or more and you're facing it, all of these are going to be engaged simultaneously. To some degree or another, they'll be touching lightly to actively cutting, so positive rake is probably essential. I also notice they're relieved doubly, and they've got a bit of a flat spot which looks like they're wiping, so they should have a really nice surface finish. Let's go check it out. So looking at this finish, I don't think they're wipers after all. I think that it's a smooth, nice flat finish, but it's nowhere near as good as a wiper finish. Ingersoll sells some APKT wipers. I might buy a couple to try out, put them in this cutter and see if I get an improvement in finish. It is kind of textured. First thing I'm going to do is drill the 3/4 inch holes here, here, and here, because after I do the slot, it'd be very difficult to drill that 1/4 inch hole, practically impossible. I think with the extra material removed this way, it'll make drilling the slot up top easier. Order is very important on these things. It's kind of like playing chess. You got to plan way ahead. If you make a mistake, you can find yourself in a real bind. So I need to find my datum points, which are the bottom of the piece and the right hand side, because you'll notice up here all of the lengths are based off of this far side and the height is based off the bottom. So I need to find those 2 datum points. So let's do that. Start with our X0. I don't know how well you'll be able to see this, but let's just I cleaned all the burrs off this. Okay, there's X0. And Y0 is right along this side. Gotta be very careful with this LED edge finder because they need an insulator to separate the top from the detecting part, because the top is one side of the circuit, the detecting part is the other side of the circuit. So this is an insulator, and I don't know what it's made out of, but it's pretty flexible. So if you touch too hard, you'll make it flex and you'll get a really inaccurate reading. So that's a downside. So prepping to drill the first hole, I noticed that I wasn't matching my marks, and I was wondering what the heck's going on, and I remembered, like a novice that I am, I almost forgot to compensate for the 200 thousandths diameter of the edge finder and subtract the 100 thousandths from each X and Y axis. So I've since gone back and done that, and now we are right on our spot. Okay, so we are going to center drill this. Then we are going to drill it undersize. Focus. We're going to drill it undersize, and then we are going to ream it. I happen to have a reamer that is 1/1000th over a quarter, so hopefully that'll allow the pin to slide in sideways without too much resistance, rather than just drill it a quarter, which probably would have been oversized anyway since they're not quite round. But we're going to do it this way. Let's go. Slow it down for the reamer. Interesting observation here. You will notice that the chips spinning around scratch the dicom. And they can do the same to your finish on softer metals, even harder ones. If you really want a nice finish, you got to be really aware of chip spinning. Alright, I'm going to go and do the other ones off camera, no reason to repeat, and we'll be back in a minute. So you're probably asking, you drilled the holes, you found the edge, you're back with the edge finder again? Why? And the answer is because I don't have a vise stop that sits outside the vise. I need to build one. Also, the parallel, see, I've only got a 1/4 inch of material that's going to remain down here, which gives the vise very little to bite on. So another thing that came up was my parallels are spaced so that based on the vise jaw depth, it's exactly at a 1/4 inch. And I didn't want the risk of accidentally hitting my vise jaws. So I had some shim stock, 15 thousandths, get that up right, and I put that under my parallels, so I am 15 thousandths under a 1/4 inch of bite on here, which also means I'm going to have to be pretty gentle about my my bites when I mill the cross piece, mill the slots in this. So let's indicate this, find my zeros, and get ready to mill. Okay, so now we're going to cut the 1/4 inch slots on both sides, and I'll do it by going all the way through the part, so it'll make it easier when I cut the center section out, less material to remove. Alright, let's give it a go. We call that our Z0. Let's try a 200 thousandths cut. Might be a bit deep. Yeah, I got a lot of stick out on the cutter. Yeah. Alright, let's pull the cutter up higher. Off we go. Let's only do 100 thousandths. First pass. Not bad. So now I'm going to go for 150 thousandths. By the way, I'm only shooting for 0.489 instead of 0.5 because this material that I was using was 3/4 of an inch thick before I surfaced it to make it flat. So I had to take, I guess, a total of 11 thousandths off of it to make it flat on both sides. So that's not a critical dimension. Yeah, so 150 thousandths, not a big problem. Okay. So we're going to try that again. Definitely got to take it easy. Carbide cutter, very brittle. Alright, let's go for 50. So now we're going to want it to 0.489, final depth. Actually, we're going to go part way there. And then I'm going to measure the depth mic. Because since I was going on the Z-axis, just touching off, I want to be close as I can. Not that it's critical again, but I just like being as accurate as I can be. That is the appealing thing about doing machining for me. Alright, so one done. I'll finish the other ones off camera so you don't have to see the repetition. Alright, so now we're going to cut the center slot, which is 360 thousandths wide. So you take 0.360, subtract the diameter of the cutter, 0.25, which leaves you with 0.11. And then you divide that by 2, which is 55 thousandths, and that means we have to go either side of the center line by 55 thousandths with this cutter to make our whole 360 thousandths wide hole. Alright, let's go. We're just going to do the center first. First pass is going to be a fairly light cut. Okay, let's go. 100,000s. Okay, finished. Next, we need to drill and tap the hole in the end, which I don't have a fixture yet. I ordered one to do it on the lathe, on the mill. I could build an adapter like in Tom's book, but I haven't done that either. So since I don't have any of those fixtures, I'm just going to use what I've got and we'll use the lathe. All right, let's move on. Okay, so I set the whole thing up by marking on the surface plate with the height gauge. I marked the center point of this hole so that I know what I'm shooting for, and you can see I'm really close. I got it close with the center, and then started with the easy two sides and made sure that there's zero. Actually, that one's off by about 1,000th, but yeah, oh, so it's a 0.5 total. So you find the low point. Then the other two sides are a little more challenging because it's not symmetrical. I'm not trying to find the center, I'm trying to offset it 260 thousandths. So here's one side, the low at 0, and the other side 262 thousandths, which is right on. So now we can drill and tap our hole and we'll be centered. Okay, so we started taking the threads off. We squared the sides. We got the last, so we're going for 150, and we are at 162. We got 12 more thousandths to come off. Start with 11, see how that works. Thousandths. Alright, let's give it a measure. This again is not a critical value. 151, wow, right on the 150. 150, alright, 150 and a half, we'll go with that. And then we need to figure out how to notch it. Okay, so here's what it is. I've got a boring cutter that'll do 37 thousandths. So I need to put a 1/16 of an inch notch in here that's half the diameter of a 1/16 inch pin, so that the two pins I'm going to put in will grab on this and hold it in place. I got to be slightly larger than that. So I'm going to use this boring bar, but since it's the angle it is, it'll become a left-handed cutter. I got to run the lathe in reverse. So it's going to be a little different than anything I've done before. That's always challenging and fun. All right. This is a very delicate solid carbide cutter, so I'm going slowly. Alright, I think that turned out pretty good. It's a little bit wider than the 1/16 inch pin. That'll give it some slop room because you don't want it to be tight. So that worked. I'm surprised and happy. Okay, we're going to drill the pinholes in the sliding piece that connects to this threaded part here. So there's going to be a hole drilled in the part that I've identified as the back. This pin on the end of the threaded part will stick into that, and then two pins will go down either side and catch this slot, hold it loosely in place so that it doesn't slide off. That part moves backwards and forwards in this slot against a piece I haven't made yet that will basically be a stop that notches into here. It's basically another little flat piece that fits inside here with a 1/4 inch dowel that catches in these spots and pushes all of the blocks together. So let's do the drilling and go from there. this next bit is to drill a .150 diameter hole 250 thousandths into the block. This is a tiny, tiny little block. You can see this is a ½ inch wide. Half inch wide. Hey, you can't even see the scale. That's a ½ inch, and this is 350 thousandths or so. The closest drill bit to 150 thousandths is .01495, and it is a 3.8 millimeter drill bit. So we're going to take this very slowly and carefully and drill. I'm using the fine quill feed because the depth is critical. Well, somewhat critical. I don't want to go all the way through it. Because this isn't a reamer and the bottom isn't flat, I want the depth of the hole to be 250 thousandths, but I'm going to need to shoot for 290 thousandths so that the flat part will go in 250 thousandths. Using the DRO on my quill feed to check that. Okay, that was it. Alright. Alright, so here I'm going to drill two pinholes, actually two holes, to allow you to remove the pins from the back. I'm going to make them slightly oversized by a 32nd. That way your alignment won't be ultra critical. Anyways, yeah, I realized once I put the pins in, won't be able to get them out. Not that's a big deal, but just in case I want to assemble, should be able to do it. Alright, good to go. That way you can knock out the pins if necessary. Alright, so onward with the assembly. Just in case you forgot, those two holes that I put in are so that at some point in the future, if I need to knock the pins out of this, I can. They have somewhere to go. I can actually knock them from the back. Alright, let's do this. So, alrighty, there we go, and this piece simply locks in at whatever position you want to be at, and you're good to go. And then you tighten this down on the blocks, which I will demonstrate in a sec. Okay, so say you had 3 blocks, and I didn't ring them together, but this way I can keep them pushed together while I'm measuring. I also noticed that the blocks are in this carbide set are various different sizes, which I thought was kind of unusual. It's almost like the carbide blanks were all different and they just used what they had. But in any case, you just set the blocks in, ring them together first, which I didn't do, and then just tighten this down and they'll be together, and hopefully I should be able to get some accurate measurements from these calipers. So let's see, that's 2.75 plus, this should be 2.95. So 2.9495. I'd say that's right on the money. If you can see that, 2.9495. That's what I'll be doing. All right. See you in part 2.